In this one page of notes for Unit 7 in AP Chemistry called Equilibrium, or your college level course in Equilibrium, we're going to talk about calculating the equilibrium constant in 7.4, but I really want to cover three main things about that. What are these equilibrium positions? How do they relate to this reaction quotient that I had in a previous video? And then how do we calculate the equilibrium constant with some fairly easy beginning problems, but using a Rice table, which is probably new, or an ICE table to your chemistry solving toolbox. All right, so let's get started with this table and see what these equilibrium positions are and how they relate to the equilibrium constant and the reaction quotient. All right, so in a previous video, I went over how to calculate reaction quotients. So I'm going to kind of run through this pretty quickly here. Reaction quotients are set up just like an equilibrium constant. So we'll have our products in the numerator, and we're doing molarities here, so that's why I have the brackets. And then the reactants go in the denominator. So it looks just like the equilibrium expression. And then you just put in the values. Now these values are pretty easy because we have 0 in the numerator and then 0.7 twice. I'm just going to say square it just to save some room. But in the end, this equals 0. And what that means is we need to make products. So this reaction will, what we'll say, shift right. We can also say that we know its Q is less than K because we have 0 as a number, okay? So let's calculate the equilibrium constant and see how it relates to this number, okay, which is obviously a 0. But this way we can figure out what the equilibrium constant value is for this reaction at a specific temperature. I am going to write this just this one time. This is going to be the equilibrium expression. You're going to notice that it's the same thing. The only difference is that we're going to be putting in equilibrium concentrations next. So I just want you to see that this is the same, looks the same, okay? All right, so then let's put in these numbers, and I've already calculated this ahead of time. So I know that that's going to be squared in the numerator. Those are our product concentration. And then it's 0.39 both times, but I'm just going to do squared because it's the same. And this approximately equals just 2.0. All right, so that's our first trial. And that's where this reaction's equilibrium constant or value lies. All right, so let's go to this next one. You'll notice that this is a little different. We have concentrations of all of our reactants and products to start with. So let's calculate our Q. I'm going to put the numbers in right away since we have the expression above. So it's 4.7 and then squared in the numerator, and then 0.43 times 0.43, so we'll just say that's squared. And what happens is the Q here, again, is approximately 120. So what that means is our Q is much greater than our K this time. And so look what happens with the equilibrium concentrations. You have the products going down in concentration, and you have the reactants going up in concentration. So let's calculate this thing called the equilibrium constant, the K. Again, I have the expression above, so I'm not going to rewrite that. I'm just going to put in the numbers, so it's 2.1, and then squared, and then 1.5 times 1.5 squared. And what you'll find is that this gives us, again, pretty much 2, or approximately 2. And that's kind of the point, is that the equilibrium constant is constant, meaning that it's constant for this reaction at a specific temperature. And so it doesn't really matter what the initial concentrations are. It's almost like the equilibrium concentrations are semi-predestined because they have to give us the same equilibrium constant, in this case 2. All right, so that's going to give us a great definition of what an equilibrium position is that if you compare, I'm just going to try to make this short, compare trial 1 and 2 with different initial concentrations, so different, and I'm just going to put concentration like with a little I, initial concentrations, the equilibrium constant, we'll just say the same number for the K value must be, I'll just say created, yeah. It's not really the best definition, but it's all right. All right, and then what about if Q is less than K? That's where we're going to basically say, later on, we're going to say just shift right. If you don't want to say shift right, you would say you want to make more. We have to make more products. And then what if Q is greater than K? I'm just going to go ditto, shift, left. And that means we need to make more reactants. And then if Q equals K, we're at equilibrium. So then you wouldn't change, the concentrations wouldn't change. And I didn't want to put that as an example in the data table, but we could. So I'm just going to put at equilibrium. I'm just going to say the concentration stay constant. Okay. All right, so on to our practice problem. I want to make sure that this stays, again, around 10 minutes for this one page of notes. So the next thing is, how do we use this thing called a Rice table, or what even is it, right? This is brand new. So R is going to stand for reaction. And if you've ever used before change after tables, BCA tables, it's kind of similar, except for these are going to reach equilibrium. And then initial is the I, and then change is the C, and then equilibrium is there. Now, some people even will do like an equilibrium with an X and then an equilibrium, the answer, like the actual concentrations. And that is something you could kind of embrace also. All right, with the example problem, so here's our example problem. What you're going to want to do is read it, and this is one of the easiest type of K equation questions, is we're given some initial concentrations of 0.25 and 0.55. So 0.25 here, molarity, or molar, and 0.55 molar. And then we don't know the initial concentration, or we just say we didn't have it. Maybe it was just 0, okay? But they did tell us that the equilibrium concentration, so I'm just going to keep it as 1E for this video. They did tell us the equilibrium concentration was 0.15. So from that, we're supposed to be able to then figure out how we can find the K value. So again, I'm going to write the K value over here, and since it's again, a molarity, it's a Kc. So you'll have your, this is methanol, concentration on the top or in the numerator, and then we'll have our carbon monoxide and our hydrogen in the denominator, but that'll have to be squared. All right, so how do we know what happened? Well, if we don't have any product, again, this is one of those where, again, Q would be less than K, so it has to shift what's called right. And then you need to use the stoichiometric ratio of 1 to 2 to 1. So we'd say we're going to lose some, so using kind of like basically algebra, lose some of the reactant carbon monoxide, lose twice as much of the hydrogen, and then we're going to gain the X. But we kind of know what X is in this case. X is this 0.15, so I'm going to put that kind of in green here. So we know that X is 0.15 because we saw that appear. So then what you can do is, if you know X is 0.15, I'm going to zoom in here. So if we know that this is 0.15, then this would be losing 0.30, and you'd subtract that amount from the above, from the initial. It's almost like, you know, it's like, to me, I always say like spending money. So you have 0.10 left here, molar, and then we have 0.25 left here, molar, and then we have the 0.15. So now we can actually substitute these in to find the K value. And since I have it written over there, I'm just going to substitute them in here. So it's 0.15, and you can put to the first power, and then 0.10 to the first power, and then 0.25. But be careful, that one would be squared. And when you check this, it gets to be 24. And so the equilibrium constant is greater than 1. So this is going to, again, going back to a separate video, trying to tie these all together, it's going to favor product production. So they might say favor product, or favors, you know, the production of more product, or favors the right side, something like that. All right, the other thing that I want to tie in from a previous video is that came from the fact that the equilibrium constant, don't forget, is a ratio of the rate constants. So it just meant that the forward rate constant is larger than the reverse rate constant. In a previous video, I sort of just like bolded that one. And that's how we end up with a K that's greater than 1. And that's just because the forward rate was more predominant in terms of the rate constant, okay? At equilibrium, the rates are equal, but the rate constant for the forward reaction was larger. All right, so hopefully that helped solve these beginning problems. I would say definitely beginning problems on calculating the equilibrium constant, knowing what the difference is between a reaction quotient versus an equilibrium position. Kind of that equilibrium constants are going to stay constant for a reaction at 8 temperatures. So no matter what we have sort of as initial concentrations, they will work themselves out to get a specific value for K. And then how to kind of start using a beginning version of a ice table or a race table. All right, well, I hope this helped you solve your chemistry problems for equilibrium, at least the start of this. And if you like this video and these one-pager of notes, please subscribe, like, and comment. And hopefully you come back and watch another one of these as I moved on to 7.5.